All right, homework out. Let's open to page 128. You do questions 21 through 24. Question number 21 asks this: how does gravitation vary with distance of separation between masses? And how is the distance between gravitationally attractive objects defined? Michael?
The greater the distance, the less gravitational force there is. The distance between gravitationally attracted objects is defined as r.
It's represented as r, but technically, do you have something to add there, you, Kendall?
Well, I said it's like a reciprocal of the masses.
Distance between their centers, technically. Distance between the centers of the objects. Not distance, for instance, between the Earth and the Moon, right? We would take the distance from the center of the Earth to the center of the Moon to find out how much gravitational attraction there is. Between you and Earth, your center, which isn't that far from your surface, to the Earth's center, there is a big difference there, right? So, anyway. Number 22, write the equation to find the universal law of gravitation, and what is the numerical value of G, Kendall?
The universal law of gravitation is F equals G times the mass 1 and mass 2 all over the radius squared, and the, what is it, like the
G, the universal, universal gravitational constant?
Is 6.673 times 10 to the negative 11 newtons times whatever.
Meters squared.
And then the kilograms squared.
Per kilogram squared. There we go. Okay, we got it out. 6.673 negative 11 newtons times meters squared per kilogram squared. And when it says define the universal law of gravitation, obviously that is that the force of gravitation is proportional to, based on the gravitational constant, the product of the two masses, and inversely proportional to the square of the distance between their centers. Number 23, why is the law of gravitation said to be universal? Audrey?
The law of gravitation is said to be universal because it describes an attraction that exists between any two masses in the universe.
Good. So theoretically, if you could survive, I don't know, way, way, way out in the universe, away from any other celestial body, and we put you in space and something else in space, no other thing, there is still going to be an attraction between you. Now, again, it'll be fairly slight, but if there's no other forces out there, it may eventually work. You could use the force, potentially, to draw whatever to you. Anyway, number 24. It's in a galaxy far, far away. What is the difference between gravity and gravitation, Michael?
Gravitation refers to the attraction between bodies, and gravity refers to planetary or celestial attraction.
Good. Gravity we use to refer to some actual celestial body, the sun, the moon, the earth, a planet, and other objects, whereas gravitation can be between any two objects, me and this book right here, however slight that attraction may be. Good. Go and set that aside. Let's go and review some things we talked about over the last several lessons. We've been talking about Sir Isaac Newton and his 3 laws of motion. Take the poster down. Audrey, what's the first law of motion? Law of inertia, which says that an object... We did. Phone a friend, Kendall.
Okay.
Kendall hung up on you.
Alright, so an object will stay at rest if no force is pushed on it.
That's half of it.
Something to do with velocity too.
Very much so.
Yep.
It will maintain its current velocity unless an outside force acts on it.
Good, which covers the rest, remember, because the zero velocity would be rest. So an object maintains its velocity unless acted upon by an outside force. What about the second law of motion? What was that all about?
Force is directly proportional to acceleration, and acceleration is directly proportional to mass.
Acceleration is directly proportional to mass?
Inversely.
Inversely proportional to mass. So really, I focused on it from the perspective of acceleration. Acceleration directly proportional to force, inversely proportional to mass. What was the equation for that?
F equals
F equals
m times a.
m times a. Good. Or if we had two different forces, masses, accelerations, whatever, Kendall.
F1 over F2 equals m1 times a1 over m2 times a2.
There we go, without having to write it on the chalkboard and then erase it. What about weight? What is weight?
What is weight?
It's what you do on women. Just kidding. What is weight? Not that. Not W-A-I-T. W-E-I-T-H-T. What is weight?
Okay. It is gravity when it applies to mass, like gravity on mass. The force of gravity on mass.
There we go. The pull of gravity on an object's mass. So how would I calculate weight, or how would I find weight of an object?
F sub W equals mg.
mg. There we go. Instead of ma, mg for weight of an object. Then we started talking. Oh, then we have the third law of motion. Let's not miss that one. What was the third law of motion, Audrey?
Said something about action reaction.
Yeah. What about action and reaction? For every action, there will be
Equal and opposite reaction.
good equal and opposite reaction. Good equal in magnitude, opposite in direction. We talked about all kinds of examples of that. Then we talked about a force that always is against us. What is always against us, Kendall? Doesn't always mean it's bad. It's just always against us. Michael?
Life.
Not life. Friction. There we go. Friction is always against us. Now, when would we encounter friction, Kendall? Or when would an object encounter friction? Michael?
When it comes in contact with another surface.
Well, not so much when it comes in contact, but if it
Slides.
slides across a surface, right? So when the little kid at the play place at Burger King spilled his honey on the slide and it stuck there and it got baked on, and you try to slide down and then you stick to the slide on the way down, it's just bad versus when it's nice and clean and smooth, you slide right down. When an object slides across the surface, friction develops. We have two different types of friction though, Kendall.
Kinetic and static.
Kinetic and static, which one's which?
Kinetic is the keep sliding, and then the static is start sliding.
Okay, with the friction that resists, because friction always resists. Resistance to start sliding, static. Resistance to keep sliding, kinetic. And we have 4 laws of friction, 4 laws of kinetic friction. Give me one of them.
You gotta have smoothness, like roughness.
Okay, the types of surfaces, the roughness or the smoothness of the surfaces rubbing against each other will affect the friction. Another law. Remember, there were 2 that said friction doesn't depend on this, and 2 that say friction does depend on this. It does depend on the roughness or smoothness of the surfaces. Kendall?
Surface area?
What about surface area?
Oh,
It does or does not depend on the surface area?
it does not.
It does not. So sitting down to put a greater surface area of your person upon the floor does not actually increase your friction. All right? Does that help trigger a bell maybe? No bell triggered.
It does not
Have
depend
laws.
on velocity.
It does not depend on the velocity either. So dragging something faster doesn't make you have less friction. It gets the job over with quicker, but it doesn't diminish the friction. There's one more thing friction does depend on. Remember, I wasn't dragging Michael around for a reason. Besides the fact that he's not on the front row, there's a desk in front of him. Besides that. Kendall?
Mass. Like weight. Something like that.
Kind of, yeah. It does kind of depend on weight.
I don't know.
But not so much the weight that bears down, but on how much force pushes back up. What do we call that upward force, class? Normal force. And the only reason I say that is because if you had a vertical surface, there is no normal force, so the weight doesn't matter at all. That's the only case in which weight wouldn't matter at all, because in any other case, the weight will affect the normal force, but it's the normal force is what determines, and if we remember that, that'll help us remember our equations. Do you remember the equations for friction? So we had a static friction and a kinetic friction. So F sub SF means force of static friction, force of kinetic friction equals. So there, right, your coefficient, mu sub S, mu sub K times F sub N, there's one of your laws. It depends on the normal force. And another law, it depends on the types of surfaces rubbing up against each other. Velocity is not in there, surface area is not in there. It doesn't depend on those 2 things. What units do we use for normal force, class? Newtons, or maybe pounds if we were US customary. So what would we use for the force of friction? Newtons or pounds. What does that mean about the coefficients?
It has no unit.
They're unitless because they don't affect the units. We also talked about ways to reduce friction. Since friction works against us. Now again, not that friction's always bad, right? In the shoe store with those leather bottom shoes, friction would have been a really good thing right then. It wasn't there when I needed it. Anyway, so what's a way to reduce friction, Michael?
Ball bearings. Inside wheels.
Okay, so using wheels, rollers, bearings, minimizing the friction by rolling in general. Good. Another way?
Choosing suitable materials.
Choosing materials that just have less friction inherently up against each other. Phone a friend?
Minimizing roughness.
Good. Sanding down or smoothing out a surface to minimize roughness. Automobile engine. Slip and slide. You ain't going to go slip and slide down the tarp by itself, are you? You put a little soapy water on there, though, and lubrication also works. Or maybe like a razor, right? We don't usually want to shave just blade on skin. Usually either water, shaving cream, shaving oil, something, right? To help lubricate the razor even so it doesn't like tear us up. So whatever, right? Lubrication minimizes friction as well. Clear, yes, except for a clean sheet of paper and a pencil. Clean sheet of paper and a pencil and a calculator. Everything else away. First last name at the top of your paper, along with today's date. First and last name. At the top of the paper, along with today's date today is 10/21/22. 10/21/22, today's date. And this is quiz 11A. Quiz 11A. Here's a quiz that Brianna had years ago. She was small too. She got all the short jokes before you came along. You remember Brianna. We remember Brianna. We loved Brianna. To give her a shout out there. All right, let's take a look at the quiz together here. Numbers 1 through 4. Completion, write the word or words or whatever should go in the blank. Notice on number 3, obviously you're going to have 2 answers because there's 2 blanks. Numbers 5 and 6, write 3 of those for 5, and for number 6, write 3 of those. So I give you a little bit of forgetfulness there. And then for 7, 8, and 9, obviously write the equation, show your work. Careful with your units and sig figs on the problem solving. All right, you may begin. Just about 2 more minutes to be finishing up. Alright, if you're still working and you're watching at home, go ahead and pause the video to give yourself time to complete the quiz. Otherwise, let's go ahead and keep on moving. Go and get your notes back out if you would please. And review what we talked about yesterday. We looked at 4 fundamental forces in nature. 4 forces that are always just there. Nothing has to be done to make them exist. They naturally exist. Give me one of the 4 fundamental forces we looked at yesterday, Kendall.
Strong.
The strong force. Where is the strong force evidenced? Where does it exist?
Center of an atom.
Good, within the, what do we call, what's at the center of an atom?
Oh, the nucleus.
Good, within the nucleus of the atom. It's what keeps the protons together, what keeps the neutrons together, what keeps the nucleus together. And what did I say to know about the strong force? There was one key thing I told you to know, besides that it's in the nucleus.
I don't know much about it.
Yeah, there's that too. It's kind of the, not sure what else to call it, but strong force. But there's a reason they call it the strong force.
It's the strongest.
It's the strongest of all the forces. So we need to know that that's the strongest of the fundamental forces. Give me another of our fundamental forces, Audrey.
Gravitational.
Gravitational force. There were a couple things I told you you needed to know about gravitational force. And you read a little bit about it last night in the reading too.
It's the weakest.
Good. It's the weakest of all of them. Okay, that's an important thing to know. Another important thing to know, Michael.
It's between everything.
That any 2 objects, always gravitational force exists, and it's always a force of, what direction does gravitational force act? I said gravitational force is a very, class, attractive force. It's always attractive, always attractive, always attracts things together, which isn't always true for the forces, right? Michael, another force.
Weak.
A weak force. What do we need to know about the weak force?
It's weak.
Weaker than what?
It's not weaker than gravitational.
It's not weaker than gravitational, though. So it's not the weakest. Strong is the strongest. Weak isn't the weakest. But it is weaker than everything other than gravitational force. Where do we think we see weak force evidenced?
In the atoms.
Radioactive.
In some forms of radioactive decay, there seems to be a non-attraction where there should be at least some based on the other force and gravitational forces, and there's not. So it's like, okay, there must be some other force in play here. We're not quite sure what it is. It's pretty weak, and we don't really see it a whole lot. We're not really sure much about it. So the weak force. And the last force that I started to say a second ago, class, was electromagnetic. Where would electromagnetic force be evidenced, Kendall? What kind of bodies, what kind of objects would have an electromagnetic force? Not overthink this now. Electromagnetic. Okay, magnetic objects, good. I don't want to get the other half.
Planets.
Oh my. Kendall, electromagnetic force. So magnetic objects, electrically charged objects, okay? So basically the way I said it, the easier way, because I'm lazy, is charged bodies. Either magnetically or electrically charged bodies will have an electromagnetic force. Is it always an attractive force? No, it turns some people off. It pushes some things away, doesn't it? Do we remember from past years when electromagnetic force is attractive? Opposites. And repulsive, when they're like charges or like poles. All right, and then we talked a little bit about just kind of laying the groundwork for what we're going to get into more today. It's something that you read about a couple nights ago. We looked at our solar system and said there's really been a couple of views down through history. And for the longest time, people believed the ideas of a Greek philosopher. And do you remember his name? Ptolemy. Ptolemy with a P, right? Ptolemy, but the P was silent. Or do you use that next time? You know, you're doing like confirmation code or whatever. Yeah, I've got A as in apple, the number 3, the number 4, the letter C as in cat, and then P as in Ptolemy. I just really mess with people. I don't know. Anyway, but what was Ptolemy's idea? What did he think based on what he observed in the night sky when he beheld the heavens? What did he think was going on up there? That the earth is the center of everything, and everything goes around us. And that was a really popular opinion for obvious reasons. I mean, we are it. That's pretty cool, but it was wrong. And who noted, made a lot of observations about the night sky and was willing to go out there and say, nope, we're not the center of everything. Who was that guy?
Copernicus.
Nicholas Copernicus. You read well? And like him in his notes there. And Nicholas Copernicus noted what is really the center of our solar system, Kendall? The sun is the center of the solar system. We go around it, as do the other planets. And just based on observation, right? Based on the way everything's moving, no, it can't be going around us. It's got to be going around something else. And that's where we pick up in your lesson then, and also on page 121. Obviously, we've seen science projects and demonstrations in elementary school, right? You got a big yellow ball, and they got little coat hangers sticking out, little other balls, colored different things, different sizes, and they spin around and stuff. Anyone do that one when you were a kid? Okay, and you guys saw other people who did it, and explain your model here. Well, the big yellow one's the sun. Okay, we're breaking some new ground, Copernicus. And these other ones, these are the planets. Anyway, and did you have Pluto? Pluto goes around the sun, but they don't call it a planet anymore. They say it's too small. I don't know. Anyway, but I digress. Obviously, Copernicus figured out everything's going around the sun, but really didn't do anything to predict how the planets move around. It's just they go around. And it's assumed then, as was the case with the geocentric proposal, that everything just moves around in circular orbits. Everything goes around in circles. But that's not quite the case. A Polish astronomer, Tycho Brahe, make sure I got his origin correct. No, he was not. He was Danish. Let's say, wait, that doesn't sound Polish. Tycho Brahe made so, or Brahe, depending on how you pronounce it. I pronounce it Brahe, but apparently it's Brahe. Tycho Brahe, whatever his name, you don't even have to know it, was a Danish guy, and he noted the movement of the planets. He was making a lot of detailed observations, making some charts, and then he died. And his student under him for about 20 years took his observations and finished making some more observations, and so he gets all the credit. And I just wanted to give a shout out to the guy whose name I can't pronounce, Tycho Brahe or Tycho Brahe, however you pronounce his name, because he was the teacher that made it possible for the more famous guy, Johann Kepler. You need to know his name, because he still gets the credit regardless, for noting 3 laws of how planets go around the sun. So 3 different laws. His first law, based on these observations, and by the way, I do want to point out, it says there the laws are empirical laws. Empirical means based on observation alone. Remember at the beginning of the year we talked about the scientific method, how just basing things off observation is really inadequate? Well, how you going to do that in a laboratory though? Right? He really had no choice. You can't do anything beyond make empirical observations here about planetary motion. But I did want to point that out. They're not experimental science, they're empirical science. The first law is called the law of orbits. That doesn't tell you anything, does it? You already knew they went around, okay? So what you need to know about the law of orbits is that the planets don't go around in perfectly circular orbits. They go around in elliptical orbits. So the orbit is in the shape of an ellipse. So law number 1 talks about how a planet goes around in the shape of an ellipse. Now what's interesting is a perfect circle, as you know from geometry, has a center point, and the distance from that center point is always the same. An ellipse also has a center point, but the distance from the center doesn't stay the same all the time. An ellipse has 2 key points inside it. We'll talk more in pre-calculus later about the ellipse, but has 2 key points inside it called focal points or foci. And the distance to one plus the distance to the other, the sum of those 2 distances will always remain the same. But what that means is there will be times where it's closer to one and further from the other, closer to the one, further from the other, right? There will be times in that. The planets go around the sun in elliptical orbits where the sun is one focal point and there's some empty point in space that is the other focal point. As the 2 points get further apart, the ellipse becomes more oval shaped. As the two foci get closer together, it becomes more circular. And if the two foci were to actually coincide, you get a perfect circle. Now, to be fair, for all of the planets, the what's called the eccentricity, you don't need to know that term, is very, very low, meaning the distance between the two foci are very, very small, particularly for planets like Earth. Our orbit is nearly circular. You could understand why people would assume it was a circle. I wrote these down. I believe it was Neptune and Venus are the other two. Yeah, Neptune and Venus are the other two that have nearly circular orbits. The most pronounced would be Pluto, if you want to call it a planet still. I learned Pluto when I was a kid, but that was 25 years ago. Anyway, moment of silence for Pluto. And that was a short moment of silence. And it's a small planet. And Mercury, actually, surprisingly enough, the closest planet, those have the most elliptical orbits, and their eccentricity is really low. That doesn't mean anything to you now. It will when we get to pre-calculus. But that just means that the points are still really close. So these aren't really exaggerated ellipses, but there are points at which, in the orbit, planets have a point closer to the sun and further from the sun. So that's law number one. The law of orbits talks about the shape being class an ellipse rather than a circle. Law number two, it's called the law of areas, and that's a really weird way to describe it. So you don't even need to really know the law of areas, but there's a really good diagram on page 122. Okay? Now, this has been exaggerated, okay? None of the planets go around in an ellipse that is this pronounced. All of the ellipses of planetary motion are more circular than what you see here. But it gives the opportunity to see this. If you were to take a random point in time on any point in the planet's orbit and draw a line to the sun, calculate a certain amount of time, and find another point, draw another line back to the sun, you would get, it's not a triangle, but it's a sector of a, not even a circle, but of an ellipse. Do that at any point, and those areas would be the same. Now, what does that mean? It means that if the radius, if you will, the distance from the sun is smaller, you would have to have a longer arc along the ellipse to make equal areas. Meaning, here's what you need to know. As a planet is closer to the sun, hold that thought, stop for a minute. As a planet's closer to the sun, in the same amount of time, it has to travel a greater distance. Closer, greater distance in the same amount of time. What does that mean? Going back to last chapter. Greater velocity. Closer to the sun, that's what you need to write down. Closer to the sun, greater velocity. Further from the sun, less velocity. Closer to sun equals greater velocity. Literally, the planet speeds up as it gets closer to the sun, and it slows down as it gets further from the sun. Now again, can you imagine if Earth had a very pronounced elliptical orbit? And there were times where the Earth sped up and slowed down pronouncedly? That would be really hard on humans, okay? I don't think it's coincidence then, not only the distance at which God placed us from the sun on average, but the fact that Earth's orbit is so nearly circular, right? Big Bang? No. Comets, for instance, go around the sun in very pronounced ellipses. You've heard of Halley's Comet, right? Every 174 years. Why? Because its ellipse is so wide. And it has a dramatic speed up and slow down as it gets nearer the sun, further from the sun. But God didn't intend life to exist on Halley's Comet, right? God intended life to exist on Earth and put it at just the right average distance with a nearly circular orbit going around. Now, a couple of points you need to know. The first point is the point where it's closest to the sun. And there's a prefix that means around or surrounding. It means it's peri, right? The pericardium is right surrounding the heart. Periosteum wraps around the bone. Perimeter goes right around the edge of... So peri has the idea of being right around or surrounding. The perihelion, remember helio refers to sun, so perihelion is the point at which a planet is closest to the sun. The point at which a planet is closest to the sun. Obviously, that would be the fastest movement of the planet. And for Earth, I believe that is January, is where Earth hits the perihelion, the closest point to the sun. Now, you say, why isn't that the hottest? Well, because of the tilt of the Earth, because of where we are. But if you were in Australia, January would be really hot, right? Why? Because that's the part of the Earth that is facing the sun or closest to the sun because of the tilt of the Earth. So anyway, so the perihelion, and then you know this, that ap or apo means away from, right? Apostate is somebody who goes away from what they were taught to believe. The aphelion is the part which it is away from the sun. Aphelion, the point furthest from the sun. Obviously, that would be where the planet moves at its slowest. Again, these points are not so drastically different in their distance from the sun that you're going to get a dramatic speed up and slow down at all. Minor speeding up and slowing down, but it's there. It was observed. Hence, we call it a law, not a theory. So the first law class says that, and this lays the groundwork for the other two, that planets go around in the shape of an ellipse, where there are two main points within the ellipse called foci, or focal points. One of those focal points is the sun, the other point is just random spot in space near the sun. All right? Rule number two then, because they go around in ellipses, there are points where they are closer and further. The point that is closest is the perihelion, and the point where it's closest is called the perihelion. And the point where it's furthest is called the aphelion. I don't know, it's a Friday, I just gotta make sure we're paying attention. All right, as a planet gets closer to the sun, it does what? Speeds up, and as it gets further, it slows down. All right, law number three. This is called the law of periods. Now, period refers to time, right? There are different time periods throughout history. Even in graphing, we were working on in pre-calculus recently, graphing trigonometric function. We talk about the period is the amount of time, if you will, along the x-axis to complete a curve. Period refers to time. So the law of periods is talking about how long does it take a planet to go all the way around. Now, this is going to be groundbreaking for you. But planets that are closer to the sun go around in less time than planets further from the sun. Now, if you've ever run around a track, you know that you want the inside lane, not the outside lane. Unless you're doing it for conditioning and training, then by all means use the outside lane. But in a race, you want the inside lane. In fact, you want the white line on the inside. In fact, if there's about 3 inches of cork or asphalt out inside the white line, you're running on that, right? You want as inside as possible. Why? Because you get around more quickly. So the law of periods, on one hand, it seems like, well, duh, but there's actually a proportional relationship. If you took the time to get around once, the time of orbit, the square is proportional to the cube of the average distance of the planet to the sun. So there's actually a math relationship. It's not just, hey, if you're closer, you get around quicker. If you're further, you take longer to get around. So the law of periods is this mathematically. Time squared is proportional to radius cubed. Now, again, it's not circular, so there's not a true radius. R means the average distance from planet to sun. So the square of the period is inversely proportional to the cube of the average distance. That's the law of periods. But practically speaking, planets that are closer get around in less time. Like Mercury, for instance, is it like 51 days to go around, but it takes like 80-something days to spin on its axis or something weird, like there are 200-something days to spin around. Ask Miss Moore, she's the astronomy person, not I. Obviously then planets further out than us, Mars, Jupiter, Saturn, Pluto, if we want to call it a planet, they would take that much longer to get around. Why? Because they're further away. Questions on Kepler's 3 laws. Pretty basic, right? Now, I want you to know, obviously we said they're empirical because they're based on, not speculation, observation. They're based on observation. It's not just pure speculation. Yeah, I think the Earth's the center of everything. It's based on my observation, this is what I've seen to be true, and no one can refute it. Everyone else says, yes, that we all agree that's what that seems to show. But again, it's not based on experimentation, but rather just observation. So we say the laws are empirical. Also, I want you to note, though, every one of these laws describes what is happening. None of them describe why it happens, correct? What do we call explanation of motion without regard to the cause? Study of motion without regard to the cause of motion. Kinematics. These are kinematic laws as well, because all they do is describe what happened. Enter Sir Isaac Newton. Never content to simply say the apple fell down, Newton instead said, why did the apple fall down and hit me on the head? Because all I did was overhead in a hot air balloon in a time travel. Anyway, no. Well, Sir Isaac Newton looks at these laws. Why does it go around in an ellipse? Why does it go faster when it's closer to the sun? Why does it take, well, obviously it takes longer to get around if it's further, but why especially these two? If it's going to speed up, that's a change in velocity, that's an increase in velocity. That's acceleration. Acceleration only happens if there's an external force. There must be some force causing this to happen. There is some force causing elliptical orbits. There is some force causing, lost train of thought. There is some force causing the acceleration at the perihelion. And there must be a lesser force at the aphelion allowing for a slowing down, right? So Sir Isaac Newton sought to explain the why and the wherefore. Well, obviously the answer is there is a force acting on the Earth as it moves around. What is that force? Gravity. Gravity pulls on the Earth. Now, why doesn't the Earth, have you ever thought about this? If the sun is so huge and has so much gravitational pull, and the Earth is comparatively tiny, but compared to us really big, and it's a gravitational pull, and they actually attract each other, why don't they just go boom? Have you ever wondered that? Kind of the same theory as if you were to take a yo-yo on your finger and spin it around and around and around, right? Why does the yo-yo stay out there? Inertia. Inertia, though, says an object goes at a straight line at a constant speed, unless it's acted upon by an outside force. With the yo-yo on your finger, why does it go around in a circle? Why doesn't it go in a straight line? What's pulling, tugging on the yo-yo? The string, which is attached to your finger. So, have you ever had the string break or slip off your finger? What happens to the yo-yo? It goes flying in a straight line at a constant speed until it crashes into mom's priceless vase, or whatever unfortunate thing happens to be in the way of the yo-yo. It's usually something that matters a lot to mom, right? The yo-yo flies off and then you're in big trouble and you're like trying to find a way to blame it on the sibling or whatever you did when you were a kid. You don't do this anymore, right?
No.
Break things with yo-yos. Okay. But we understand it's the string that pulls on the yo-yo that keeps it going in a circle. If the string breaks, yo-yo flies out. But yo-yo does not, unless you're doing the around the world trick where it comes back to your hand. Yo-yo, as long as you keep a little bit of force moving there, its inertia will keep it going around and around. Inertia would cause the Earth to go in a straight line at a constant speed, but there's this tug by the sun that pulls it back in, constantly pulling it back in. As it's pulled back in, it will be pulled in a little bit closer to the sun. But as it does, where there's greater force, greater acceleration, and it actually accelerates past the sun, going very quickly. And then as it develops more and more acceleration at the perihelion, it gets more of an inertia, which pulls it away from the sun. And then it begins to slow back down as the sun pulls it back in. And that's why the elliptical orbit. Now again, it's not a dramatic effect. It's more circular than full ellipse. But that's the reason why you've got inertia, first law of motion, and you've got the outside force of gravity, second law of motion, causing this acceleration. Does that make sense? I still remember when I was learning this in college physics. I learned it in high school physics. We talk about college physics is really what I'm teaching you over again, okay, with a few more things. But in college physics, I had right after lunch, I had class, and the room was kind of warm. And so I'd eaten lunch. I'm tired, it's warm in there. And I remember I was sitting right on the front row, which is a bad spot to be, Kendall. And I'm sitting there and I'm kind of like half dozing apparently. I didn't really know what was going on, but then I was said, Robert, come on up here. Well, I heard my name, so I woke up and I kind of stumbled out of my seat up to the front of the class. Next thing I know, the professor has grabbed my hands and it's like swinging me around the classroom. And I get back to my seat and just look at the girl next to me like, what just happened? I found out later he was talking about this, how gravity pulls back in and then lets it go out. I'm not going to do that to you, Kendall. But anyway, yeah, so the point of the story is it doesn't pay to fall asleep in a physics class because you never know what could happen to you. So anyway, I have vivid memory of that lesson now because I was like, whoa, I was very confused for a little bit there. But anyway, that's the reason behind all of it. So Newton comes out with a dynamic approach that brings us to the universal law of gravitation. Now again, third law of motion, there's an equal and opposite reaction force, right? As the sun tugs on the Earth also has to then, based on the third law, tug back on the sun. So why doesn't the sun move?
It's bigger.
It's bigger. If I were to grab Kendall up here and we're spinning her around, Kendall would not move me. I would move Kendall, okay? I've got almost double her mass, okay? I'm not budging. She's budging, right? I remember there was one time, my wife had a PE class in college, and the PE teacher, like PE teachers ought to be in good physical condition, or at least look like they are. This guy wasn't. He was huge. And then she had another PE teacher who was like just huge, just massive guy. He wasn't fat. He was massive. Anyway, there was one time, I don't remember which one it was she had, but she, I guess, wasn't watching where she was going or something, and she ran into him, just boom. He didn't even budge. Okay, Earth ain't budging, or Sun ain't budging. Earth is moving, right? Earth is so much smaller. Earth moves. But there is even the third law there too as well. Universal law of gravitation says any two masses will attract each other. Now, what is this dependent on? Well, bigger objects will have a bigger attraction to each other. That makes pretty good sense. Okay, that's one thing Newton found. Another thing he found is the further apart they are, the less attraction there is. So there's less of a pull on, say, Pluto, who's further out. There's still a pull, but it's less of a pull, which doesn't cause it to move as quickly. Does that make sense? So if we say that the gravitational force, don't write this down, is proportional to the product of the two masses, if we say that it's inversely proportional to the square of the distance between them, then we can say it's equal to the product of the masses divided by the square of the distance between them times some constant value. What is that constant value? Well, we represent it with a capital G. So we've seen constants before, like Young's modulus was a constant, shear modulus was a constant. This is a constant of proportionality called the gravitational constant. We'll talk in our next lesson about how they calculated this, but they found that at 6.673, E negative 11, now watch the units, we want newtons, we want to cancel square meters, and we want to cancel kilograms squared. And there's a number for you to know. So if you will, you don't have to write this down, get this down under universal law of gravitation. And we'll have to stop there. We're going to look at one example problem before we wrap up. We'll look at it in our next lesson. No written homework tonight. Study over the content from the last couple of days. Everything that wasn't just quizzed, unless you felt really... Do you feel like we did pretty well on the quiz? Okay, good. Then study what you learned since the quiz. We have a test coming up on Wednesday. That's lesson 57. Wednesday over chapters 7 and 8. So we'll be finishing up the chapter Monday, Tuesday reviewing, Wednesday test over chapters 7 and 8. All right, have a wonderful weekend, and you are dismissed.